Hi everyone, today's lesson is going to cover using the cast rules and the special triangles in radians to solve trigonometric expressions using radians and exact values. So a couple things that we need to recall in order to do this lesson are the special triangles, which I go over in my radian measure lesson. So this is what we would call the 30, 60, 90 triangle, but in radians. And that comes from half of an equilateral triangle. And this one is from an isosceles triangle. It was in our grade 11 math class, the 45, 45, 90 triangle. And these are the side measurements. So we're going to use these to solve our problems today. The other thing that we went over in the radian measure lesson is the unit circle. So the unit circle shows us how the degrees and the radians here are related. Okay, so here we can see, for instance, that 30 is pi over 6 radians, 60 is pi over 3, and so on. These we'll talk more in depth in our next lesson, but you can actually use these points, these coordinates here, which represent cos theta and sine theta of your angle as the x and y coordinates of these points at these locations. And they can actually be used very quickly to solve trigonometric expressions as well. Okay, so let's get into it. Okay, so our task is going to be to find the exact values for each trig ratio. You should not have to use your calculator for this, though if you want to place your calculator in radian mode, you can use your calculator to check your answer at the end. What we're going to do is figure out the exact value of these trigonometric expressions using the unit circle and using the special triangles. And I've got some steps here for us to follow as well. So firstly, we're going to place the angle that we're working with. So for instance, in the first one, that would be 5 pi over 6 into the correct quadrant. Yesterday when we did the radian measure lesson, or if you go back and watch that lesson video, I discussed how pi over 6, which is 30, actually means that we can cut each quadrant into 3 equal pi slices, and we can actually count up by pi over 6s when we do that. So this is like 1 pi over 6. This is like 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6. And of course we can reduce these and continue on from there. But there's our 5 pi over 6 measurement. We don't need the rest of them, but it can just be helpful to kind of think out that process. So we can get rid of these. We don't really need those. But there's our 5 pi over 6. And the nice thing about working in radians is that when we form the triangle and figure out the reference angle, it's actually quite easy to find because we can actually see the reference angle directly in the radian measure itself, which is actually pi over 6. So just as a recap from grade 11, when we did this in degrees, we were always making the triangle with the closest horizontal. That's going to allow us to find the correct reference angle. So we create a right angle triangle, and the reference angle is always this interior angle here, which is actually pi over 6. It's 30, the equivalent of 30 degrees when we were working in degrees. Now, how do I know that? Well, I know that because, as we said, this over here is 6 pi over 6, or in other words, pi. So if I know that this is 5 pi over 6, and I know that the whole thing, this is 6 pi over 6, I can find this extra little slice by just simply doing 6 pi over 6 minus 5 pi over 6, and that's going to give me pi over 6, of course. Okay, 6 pi minus 5 pi is just 1 pi. So that's how we can confirm that. But we're always really going to be able to see that reference angle inside of the radian measure there. So that's kind of nice. All right, so from there, we're going to label our special triangle based on pi over 6 being in this corner right here. So Pi over 6 is the smallest angle of the triangle. So the opposite side to this is 1, the adjacent side is root 3, and the hypotenuse is 2. And again, we went over that in the radian measure lesson. If you're confused as to where these values are coming from, I would suggest you go back and take a look at that lesson. Okay, and of course that's pi over 3. We don't really need it because we're going to be utilizing this as our main reference angle. All right, so we have placed the angle, we've formed the triangle and the reference angle. Now we're just going to calculate the ratio using the reference angle and the special triangle. Another thing that we want to do as we're doing that is use the cast rule to determine the sine. So if we remember from our grade 11 trigonometry lessons, we use the word cast as an abbreviation starting in the 4th quadrant, working our way counterclockwise in order to determine which trig ratios are positive in which quadrants. So we are in the S quadrant, which means that sine is positive here and the other trig ratios are negative, other than its reciprocal, of course. Its reciprocal will also be positive here. So if I'm taking the sine of something in the sine quadrant, I'm actually going to get a positive answer out of this. And sine is opposite over hypotenuse when we think about SOHCAHTOA. So if this is my reference angle, that makes this opposite and this hypotenuse. I am positive because I'm in the sine quadrant, so this gives me positive 1 over 2 as the answer. And that will be my final answer. So I did 3 and 4 together there. Okay. Now, if we look at the unit circle, I'll show you kind of an interesting thing. If you get to know how to use these points, which I'll explain further in my next lesson, if you look at the pi over 6 location and you look, or sorry, the 5 pi over 6 location, and you look at the y coordinate at that location, that actually tells you the value of sine pi over 5 pi over 6 at this specific radian measure value. This tells us, the x-coordinate tells us the cos of 5 pi over 6 at this specific value of this is specific radian measurement. So if you know the unit circle, you can actually answer these questions fairly quickly. All right, next one, cosecant of 7 pi over 4. So if I'm trying to figure out where 7 pi over 4 falls, I can certainly switch 7 pi over 4 into degrees if I want, or I can split each quadrant into 2 equal pi slices. So the top has 4, 1, 2, 3, 4. The bottom will have another 4 here, 1, 2, 3, 4, 5, 6, 7, 8, and that will give me a full rotation around. Now, pi over 4, it's important to remember that that's 45 degrees, right? So if this is 90, that means this is 45 and this is 45. So if I simply count up, this will be 1 pi over 4, 2 pi over 4, 3 pi over 4, and so on. Don't forget to label these as well. And of course, if anything can be reduced afterwards, you can reduce it if you're doing a full labeling. Sorry, I keep hitting my water bottle here. So there's 7 pi over 4 right there. It falls right in the center of the last quadrant. The rest, goodbye. We don't need it. Just using that for counting. And as you get more familiar with where to place all of these values, you don't, of course, have to do that. But if you can kind of get to know where each of them are placed, that will help you to go really fast in these questions. Okay, so we place the angle. We're going to go to step 2, form a triangle, and figure out the reference angle. So the triangle is also always made with the closest horizontal. I know somebody on this test is going to make a triangle that goes like this. Okay, don't be that guy or that gal. Please make sure you make it with the closest horizontal. I don't want to write on anybody's test, you did the thing. Don't do it. All right, and as I mentioned, we can actually see our radian measure right in there. It's pi over 4. If you want, you can label this as 8 pi over 4 and simply subtract 8 pi over 4 and 7 pi over 4, and that will give you the reference angle of pi over 4. All right, so that means we're working with the pi over 4, pi over 4, pi over 2 triangle, which makes our side measurements 1, 1, and root 2. Okay, I'm also going to use the cast rule here, so we're going to write out the cast rule. And we are in the cosine quadrant. So that means cosine and its reciprocal are positive here. Now, cosecant is a reciprocal ratio, or a secondary trig ratio, as we would call it. It is the reciprocal of sine. So if sine is negative here and tan is negative here, that means their reciprocals are also negative here. So cosecant of 7 pi over 4 is actually going to give us a negative answer. And because sine is opposite over hypotenuse, for this one, I would be looking for hypotenuse over opposite. So here, remember, this interior angle is your reference angle. Here, opposite over hypotenuse is 1 over 2, and its reciprocal, hypotenuse over opposite, is root 2 over 1, which will, of course, just reduce to negative root 2. One other thing that your teacher might do, if you're watching this video and you're not one of my students, is your teacher might actually just forego the idea of using the cast rule and tell you to think with your mind and think about whether this is positive or negative. And of course, if I go right on the x-axis, this is positive, so that would be positive 1. But if I go down, that of course makes the 1 here negative. So if I go down on the y-axis, I'm going into the negative. So really this is negative 1. So when I calculate this, I actually get root 2 over negative 1, which simplifies to negative root 2. And this is why certain trig ratios are positive and negative in certain quadrants. Because, of course, here the x's are negative, here the y's are negative, here the y's are positive, and here the x's are positive. So you can use that idea to kind of help you with your ratios as well, if you want to think about it that way. I won't do that and also the cast rule. I will do one or the other if I'm deciding. Okay, let's do a few more together. So 11 pi over 6. So if you want, you can separate the top into 6 equal sections and the bottom into 6 equal sections. This is 12 pi over 6, or in other words, 2 pi. So 11 pi over 6 comes just before that over here in the fourth quadrant. Okay, and my reference angle is pi over 6. We're going to create that special triangle with the closest horizontal because we don't want to be that person that does it with the vertical. And we'll label the sides accordingly. So across from pi over 6 is always the smallest side because pi over 6 is the smallest angle. The adjacent is root 3 and the hypotenuse is 2. I'm in the cosine quadrant, and I'm taking the tan of something in the cosine quadrant, so I expect my answer to be negative. And tan, using SOHCAHTOA, uses opposite and adjacent. Okay, remember I'm labeling based on this angle right here. So this is opposite, and this is adjacent to that angle. Okay, so opposite over adjacent, I'm going to get negative 1 over root 3. Now, if you plug this into your calculator, you're going to see that you get negative root 3 over 3. Those are actually the same decimal value. If you change those into decimal values, you'll see that they actually equal the same thing. The reason is because we do something in math called rationalizing the denominator. That involves getting roots out of the denominator. So I'm completely fine with this answer if you want to give me this answer, but I do want you to know why your calculator is giving you out what it's giving you. And the reason for that is that technically we don't like to state roots as denominators in math. So I will simply multiply the bottom and the top by the root that's in the denominator in order to fix this. And that gives me 1 times root 3, which is just root 3. And root 3 times root 3 is root 3 squared. So the squared and the root cancel, just giving me 3. So both of these answers would be acceptable, provided that you, of course, support your answer. And if you're going to give me this answer, I know that your calculator knows how to give you out that answer, so I want to see how you rationalize the denominator. All right, let's go to secant of 3 pi over 4. So this is where I will separate the top into 4 equal sections. 1, 2, 3. There it is right there. 3 pi over 4. I don't need the rest of this, so we can get rid of that. Triangle is always made with that horizontal line, so that's going to be there. And my reference angle is seen in the question. It's pi over 4. All right, so let's use the 1, 1, root 2 triangle and the cast rule. So I am taking the secant of something in the sine quadrant. Secant is the reciprocal of cosine. So if sine is positive here, that means cos and tan are negative along with their reciprocals. So I'm going to say cos is negative here. So my answer should be negative. And cosine, as we know from SOHCAHTOA, is adjacent over hypotenuse, making secant hypotenuse over adjacent. So here's the adjacent side right here. Here's the hypotenuse. So I should get root 2 over 1, which of course, again, simplifies to negative root 2. All right. Find the value of all 6 trig ratios for 5 pi over 3. Now, when I see pi over 3, this is just a simplified version of a pi over 6 measurement. So I want to think about this if I'm placing it around using the method that I'm showing you as 10 pi over 6. So 1, 2, 3, 4, 5, 6 equal slices, 7, 8, 9, 10. There it is right there. 10 pi over 6, which is 5 pi over 3. Now I'm just going to think about it as 10 pi over 6 for placing it when I divide everything, the top and bottom, into those 6 equal quadrants. But I will think about it as 5 pi over 3 when I decide on my reference angle here. Okay, so pi over 3 will be my reference angle, which always goes in this interior corner here, and I'll label my sides accordingly. So this is going to be 1 this time, this will be root 3, and this will be 2. Root 3 is always across from pi over 3, and 1 is always across from pi over 6 in this triangle. The hypotenuse is always 2. Okay, so now, given that I'm in the cosine quadrant, thinking about the cast rule, I know that cosine and its reciprocal, which is secant, are positive here. Everything else is negative. So let's set up all 6 trig ratios. Sine 5 pi over 3. This is going to be opposite over hypotenuse. This one's adjacent. We'll need that for later. And it will be negative in the cosine quadrant. So negative root 3 opposite over hypotenuse 2. Once I have that, its reciprocal is very easy. I don't really even need to think about it. All I'm going to do is flip it. Okay, and of course you can certainly rationalize the denominator. I'm fine with this kind of answer, but if you plug this into your calculator, it would rationalize it. All right, cosine, we know, as we said, is positive in this quadrant, and cosine, thinking about SOHCAHTOA, is adjacent over hypotenuse, so 1 over 2. Its reciprocal is secant. So that's going to give me 2 over 1, which will simplify to 2. Okay, and then finally tan and its reciprocal, tan of 5 pi over 3. So SOHCAHTOA, TOA, opposite over adjacent, and it is negative here. So that will simplify to negative root 3. And its reciprocal is cotangent. So cotangent of 5 pi over 3 will, if we're looking at this one, which is maybe easier to think about, is negative 1 over root 3. Should be adjacent over opposite. And those are all 6 of the trig ratio values for 5 pi over 3. Okay, and we're going to do an application, and we will be finished. Nicole is flying a kite at the end of a 50-meter string. The sun is directly overhead, and the string makes an angle of pi over 6 with the ground. Okay, so let's say Nicole is over here. The kite is somewhere up here, and the angle that's made is an angle of pi over 6 with the ground. So this is going to be our ground, and we'll have some kind of line, that invisible line that kind of comes down to the ground that can make a right angle there as well. So this is pi over 6. We also know that the kite string is 50 meters long. The wind speed increases and the kite flies higher until the string makes an angle of pi over 3 with the ground. Okay, so imagine that the wind speed increases. The wind's going to be blowing, and the kite is then going to go higher into the air. Here's our new kite. It's up in the air. The string is still the same, except for likely straight. And then again, we have that invisible line that goes down and makes that right angle with the ground. So this whole angle here is going to be pi over 3. I'm just going to label that off to the side here. The kite string is still 50 meters. Determine an expression for the exact horizontal distance between the two positions of the kite along the ground. So horizontal distance means to the left and to the right. So really what I want to know is how far has it moved from here to here. That's going to be called my x for this. Now in order to find x, I will likely need to know what is this full length. So perhaps we can call that y. And I will also need to know what is the exact value of this length right here, which maybe we can call z. All right, so there we have it. Let's think about as well maybe the relationship between x, y, and z. So ultimately what I want to solve here is what x is equal to. So of course x is going to be equal to the longer length y minus that smaller length z. So y minus z is the goal of what I'm looking for in this question. So I'm going to use the idea of maybe similar triangles for one of these, and then I'll show you how we can set up a trig ratio for the other one. But of course you can use either method for each of these. So let's start with the black triangle that I created here. Sometimes it's easiest just to separate these out into their own individual triangles as you try and solve here. Okay, so here's my first one. These are not to scale, by the way. It's just me kind of drawing. Here's the kite up here. Here's Nicole. We labeled this y, and we know that this is 50 meters. Now, the small version, I'm going to show you how to use similar triangles for this. The smallest version of this triangle, without us going into decimal sides, is the 1√3 2 triangle. Okay, where this is 1√3 and 2. And all I really need to do in order to figure out y is figure out what's the scale factor to get me from this mini version, or the simplest version of this triangle, to this. Well, this side right here corresponds to this. So of course, to get from 2 to 50, all I need to do is do 50 divided by 2, and that gives me the scale factor of 25. So if I do a similar thing over here and multiply by 25, this must mean that y is equal to 25 times √3 meters. And that gives me an exact value for that y. Okay, another way to do this, I'll show you with the blue triangle, is to actually set up a trig ratio and solve with the special triangle. So we're still using the special triangle either way here. So let's take the blue triangle out here. If I can get my pen to work, there we go. And this is where we have pi over 3 in here. We called this length z. This is still 50 meters. Nicole's down here. The kite's now up here. All right, let's look at how we could set up an expression for this. So if this is my reference angle, this is adjacent, and this is hypotenuse. So I'm going to use cosine, and I'm going to say cosine of pi over 3 is equal to adjacent, which is z, over hypotenuse, which is 50. And I would simply then just use the special triangle to plug in the exact value of cos pi over 3. So cosine of pi over 3 using the special triangle, I still need to use the smallest version of this triangle. This is pi over 3 over here. If I were doing cosine of that, I'd get adjacent over hypotenuse, which is 1 over 2. I find the scale factor thing to be a little bit easier, but certainly you can do this with either method and then just solve for z in this case. So probably the easiest way to then go about this is just to multiply 50 on each side. And 50 divided by 2 is just going to give us 25 meters. Okay, so just as a recap, we were ultimately trying to solve y minus z to get us x. So let's use that. X equals y minus z. Y is 25 root 3 meters minus 25 meters. Now, the best way that we can write this in the most simple form, and if you plug this into your calculator, it would likely do this as well, is to common factor out any common factors. So I see that there's a 25 in here and a 25 in here. So you will likely see, if you're looking in a textbook or in a worksheet, that it will factor that out, and then you'd be left with root 3 minus 1 meters. And that would give us the exact expression for the difference between the positions of the kite horizontally. Now, if I was looking for vertical, some questions might ask you something like that. I would just be looking for the difference between these two positions. So this length here. So I would find this one, and I would find this one, and I would subtract them. Hope this lesson was helpful for you.